Okay, can you see my screen?
Yes, it says
Okay.
Zoom to YouTube.
I'm sorry?
We can see it.
You didn't see it?
Yes, we can see what you're doing.
Oh, okay, good. I didn't hear it clear. Okay. So let me backtrack a bit. I apologize again. I keep forgetting to do that minor stuff. So let me go back to what I was saying here. So dispersion forces are the forces that exist as a result of induced dipoles that are instantaneous, right? So as shown here, this is the unpolarized molecule, right? And in an instant, it can form a dipole, and that's because of the constant movement of electrons, right? So at one instant, you may have a separation of charge where one end is negative and the other end is positive. And when that is lined up against another molecule, it can induce a dipole in the next molecule. So therefore, if this is the initial molecule that is undergoing the instantaneous formation of a dipole, then that can induce a dipole in the next molecule. And you have an attractive force between the opposite poles here. And therefore, that would be called the dispersion force, which, by the way, is also called London forces. All right. So dispersion forces, London forces are basically the same thing. And I mentioned in this page here that the strength of this force is dependent on the polarizability of the atom or molecule, which basically is talking about the ease with which the electrons in a nonpolar molecule will shift in one direction or the other as a result of the presence of another dipole close to it. So as I was mentioning here, let me take this aside here. I was mentioning that iodine has a higher boiling point compared to hydrogen, because even though both molecules are nonpolar, because iodine is larger in size and more polarizable, then the dispersion forces between the molecules in the case of iodine will be greater compared to hydrogen. And therefore, that's why iodine will have a higher boiling point compared to hydrogen, all right? Okay, so the next, I was saying that I should move this page here. So let me move this down, I think, to here. Okay, yes. So let me talk about the next type of intermolecular force, I'm sorry. And that would be the force of attraction that would exist between permanent dipoles, all right? So we're talking about molecules like, for example, let me think of one here, like formaldehyde, which has this Lewis structure here, all right? This is a polar molecule, all right? So we're talking about molecules such as ones like these, which have a permanent dipole. And what you'll find is that in these molecules, they line up such that the negative end of the permanent dipole will be attracted to the positive end of another permanent dipole. And that continues throughout the whole substance, all right? And the attractive force here, of course, would be what we call the dipole-dipole forces, all right? And what you'll find typically is that dipole-dipole forces are stronger compared to the London forces, all right? So as I said before, that happens in molecules such as formaldehyde, or if you're looking at some diatomic molecules, like, what's that example? Like bromine iodide, for example, that's a diatomic molecule, which is of course polar. So in the case of all molecules where you have a polar structure, permanent polar structure, then basically this would be the type of force that would predominate in these substances, all right? Okay, so we can predict the physical properties of molecular substances based on the different types of forces that exist, all right? So we talked about dispersion forces, which are, as I said before, these are always present, right? Every molecular compound will have dispersion forces between the molecules in that compound, right? And what you'll find is that these forces become stronger with increasing molar mass and also with elongation of molecules, all right? So we kind of referred to the increase in molar mass before because we talked about the fact that iodine will have stronger dispersion forces compared to H2, for example, right? So the molar mass of iodine is much larger. I think it's, what's 2 times 127, whatever that gives you. Let me do a quick calculation here. 2 times 127. So the molar mass of iodine is 254 grams per mole. And in case of hydrogen, the molar mass is 2.016 grams per mole. All right. So basically, if you're comparing two molecules or more that are nonpolar, generally speaking, the one with the higher molar mass will be the one which have the stronger dispersion forces. All right. Now, this part here, elongation of molecules, refers primarily to organic molecules. And we're going to see examples of that in the next slide. All right. So as stated here, in comparing nonpolar substances, molar mass and molecular shape are the essential influencing factors in terms of whether or not you have stronger dispersion forces. Then when we get to polar molecules, of course, the major forces that you'll find in those substances would be dipole-dipole and dipole-induced dipole. And this is particularly true in the case of some solutions, all right? So these are the main forces that would exist in polar substances. And what you see here is that in terms of the strength of these forces, the more polar the substance, in other words, the greater the dipole moment, then the stronger the intermolecular force is expected to be, all right? So in the case of dipole-dipole interactions, the main thing you look at in order to predict which intermolecular force will be greater than which when you compare for different molecules is the dipole moment. The larger the dipole moment, the greater would be the intermolecular force, all right? So to illustrate what I was talking about with respect to dispersion forces and elongation, here we have two organic molecules. Now, if you look at them, if you count them up in terms of the number of carbon and hydrogen atoms, they have the same molecular formula. The formula for both of them would be C8H18, all right? So one of them is octane and the other one is known as isooctane, all right? And if you compare their structures, you'll see that in this case, you have basically a chain of carbon atoms in sequence, all right? And then in this case, you have 1, 2, 3, 4, 5 carbon atoms in sequence, and then you have branching off the chains, which contains, these branches consist of these CH3 units, all right? So therefore, obviously, this one is branched, has a more branched structure, and this one is more, I don't know if this is not actually accurate because it's not actually linear, but I'm just going to use linear here for the time being, all right? So what you'll find is that the the dispersion forces in the case of the linear one is greater. So this has a greater dispersion forces, all right? While this one, the dispersion forces would be weaker. So let me put weaker here. And the reason why is because in the case of the first one, because it's a chain of 8 carbons, one after the other, when the resulting molecules would be closer on average to each other. They will lie on top of each other more closely, and therefore the forces of attraction, the dispersion forces, would be greater in the case of the linear structure. Now, in the case of the branch structure, because of the branches, the packing of these molecules will not be as efficient, all right? And as a result, the forces between the molecules will be weaker. So therefore, what you'll find is that the melting point and the boiling point of octane, because of the stronger dispersion forces, would be greater compared to the boiling point and melting point of isooctane, because the dispersion forces will be weaker in that particular molecule, all right? So when it comes to comparing dispersion forces in relations to whether or not branches exist in molecules, this applies to basically organic molecules, all right? You don't have many compounds that form chains as in the case of organic molecules, okay? So that's as far as comparing dispersion forces to the structure of organic compounds. Okay, So this is just mentioning something I said before. I don't think this is really applicable to what we were talking about here, because the polarizability has very little to do with the difference between the boiling points or melting points between these two molecules. So let me move to the next slide. So for the next slide now, we're going to talk about a particular very important type of intermolecular force, all right? And this is called the hydrogen bond. And let me just say that this term hydrogen bond is a bit of a misnomer because it's not a bond in the same sense as an ionic bond or a covalent bond, where you have sharing of electrons in the case of covalent bonds, or you have the transfer of electrons in the case of ionic bonds, all right? This is an intermolecular force. In fact, truth be told, it is actually a dipole-dipole force, but it's a particularly strong and unusual force. So the hydrogen bond, what you'll find is that that particular intermolecular force is more strong than a typical dipole-dipole interaction. So how does a hydrogen bond form? Well, basically, a hydrogen bond is formed when you have hydrogen bonded to one of these three electronegative atoms. These are the three most electronegative elements, right? If you have a compound where hydrogen is bonded to nitrogen, oxygen, or fluorine, then those compounds will exhibit hydrogen bond or hydrogen bonding. So let me use the water molecule as an example, all right, of how the hydrogen bonds are formed. So here is basically showing you, this diagram here is showing you how the hydrogen bonds are formed. So if you focus on this particular water molecule, the red is the oxygen and the two white atoms are the hydrogen atoms, all right? So what will happen is that the oxygen atom will be strongly electronegative. So let me put this right here to indicate that it has a net negative charge, partial. And the hydrogen atom here will be partially positive. All right. Now, if you remember, hydrogen has only one electron, right? So that electron will be pulled towards the oxygen that it's bonded to, all right? So therefore, this is basically barely, it's almost a bare nucleus. So let me write here, almost a bare nucleus. Because remember, the hydrogen has only one electron. That electron is being pulled away from it by the oxygen here. So because this is almost a bare nucleus, the charge density here is very high, and therefore it's going to have a relatively strong attraction for the negatively charged oxygen atom from another molecule. So this bond here is the resulting hydrogen bond, all right? And that is true for the other bonds as well. Basically, that's how these intermolecular forces are formed as a result of the strong attraction between the electronegative oxygen of one atom and the electron deficient hydrogen of the other atom, which is almost a bare nucleus, all right? So as a result, this bond is ready, and I keep saying bond because it's not really a bond, it's actually an intermolecular force, but that's a term that is used in this context. So this hydrogen bond here is relatively strong compared to any other dipole-dipole interaction. Now, that imparts certain properties to compounds where these bonds exist. For example, in the case of water, the reason why water has a boiling point, which is relatively high, which is 100 degrees Celsius, is because of the hydrogen bond, all right? If the hydrogen bond does not exist, then water would not be a liquid under normal room temperature conditions. And this has profound consequences in terms of our lives on Earth. For example, if it wasn't for the hydrogen bond, we would not have rivers or seas. The rain, well, there will be no rain formation, so we would not have rain. And therefore, of course, human life and other life, life in general would not exist on Earth, all right? So basically our very lives as living beings is highly dependent on the existence of this strong intermolecular force between the water molecules, all right? Okay, so another consequence of hydrogen bonding is that if you look at the formation of ice at the microscopic level, you'll see that it forms a very wide open structure, and that basically leads to the formation of the sort of designs that you see here in snowflakes, for example, all right? And the hydrogen bonding is very important in this regard because basically, as a result of the connections of the hydrogen bonding, it leads to a very open structure, which actually leads to also ice having a lower density compared to water, all right? The density of ice is about 90% that of water, liquid H2O. And that's the reason why ice floats. Basically, if you look at ice floating in water, you'll see that about 10% or less than 10% of the ice, of the piece of ice would actually be above water, all right? So the bulk of the mass of the ice would be below the water surface, but it would still be floating, all right? So that's another consequence of the hydrogen bonding. Okay, so this is just saying what I just said, that solid water is less dense than liquid water due to hydrogen bonding. And as I said before, and let me write it down here. I should have typed it in here. Let me put in parentheses here, density of ice is approximately 0.9 grams per mil, all right? So as I said before, this is the reason why ice is less dense than liquid water and therefore ice floats. I mentioned this already, no harm in repeating this again. Hydrogen bonding is also responsible for the high boiling point of water. I talked about that already. And also when it comes to protein structures, hydrogen bonding is very important. I don't know if you have met this in biology, but you know, in the case of proteins, you have the primary, secondary, tertiary structures. The secondary and tertiary structures are basically held together by hydrogen bonding. And you see that example shown in this diagram here. Basically, you have, of course, a very complex organic molecule. I think this is actually an amino acid, or protein, I should say. And holding the structure of the protein together, the DNA structure in this case, are hydrogen bonds, like for example, between this oxygen and this hydrogen, between this hydrogen and this oxygen, between this hydrogen and this oxygen, and so on and so forth, all right? And these are called intramolecular hydrogen bonding because these are hydrogen bonding that exists between oxygens and hydrogens within the same molecule, all right? So hydrogen bonding, again, is playing a very important role in terms of the structures of proteins, which of course are essential for the support of life in plants and animals. Okay, another demonstration of hydrogen bonding is the formation of dimers among organic acids. Dimers are basically two molecules that are basically intimately connected with each other. And an example of this is acetic acid. Acetic acid, you may or may not know, is the active ingredient in vinegar. Vinegar is about 5% acetic acid, all right? And if you look at the structure that is shown here, you have one acetic acid molecule being shown here, another acetic acid molecule being shown here. Now, let me just say this. If you take pure acetic acid, and there are experiments that have been done on pure acetic acid to show that the molar mass of pure acetic acid is about 120. The reason why that is because the actual molar mass of one acetic acid molecule is about 60, right? So for this, it's about 60, and for this molecule, it's about 60. But because of the hydrogen bonding that exists here and here, between the hydrogen and oxygen here and here, and here and here, as a result, in pure acetic acid, it exists as this dimer unit, 2 units of acetic acid molecules, right? And therefore, when experiments were done to measure the molar mass of acetic acid, you see that the molar mass of acetic acid is actually doubled to about 120 grams per mole, all right? So that's basically another effect of hydrogen bonding, the formation of dimers between molecules of organic acids. And also within one molecule, you can have intramolecular hydrogen bonding, such as this. Now, this structure here is the structure of the molecule known as salicylic acid. And if you know anything about this acid is used to prepare aspirin. And you'll notice that in this structure, you have a hydrogen bond, between this oxygen here and this hydrogen. So in some molecules, you can have what we call intramolecular intermolecular hydrogen bonding. Okay, so that's another demonstration of hydrogen bonding. All right, so some other effects of hydrogen bonding. One of them is called surface tension, which is by definition, the amount of work that is required to extend or spread a liquid surface and is usually expressed in joules per meter squared, all right? So that is what the surface tension is. And what you'll find in the case of hydrogen bonding is that the surface tension is affected such that the greater, because of the hydrogen bonding, the surface tension tend to be greater, all right? So that is demonstrated in these two diagrams right here. If you take one particular water molecule beneath the surface, you'll see that the forces of attraction due to hydrogen bonding will be dispersed around it rather evenly. If you take the water molecule at the surface, then it will only be attracted to the water molecules beside it and beneath it, but there are no water molecules above it, above the surface. And therefore the consequence of that is that more energy is needed to separate the water molecules as it spreads along the surface, all right? So that's what surface tension is all about. And the result of surface tension is that it imparts a kind of skin-like property on the water surface such that bugs, such as the one that you see here, can actually walk on water because of the skin-like surface of water resulting from surface tension. Another demonstration of hydrogen bonding is the existence of what we call adhesive forces and cohesive forces. So these are the definition of these two forces. Cohesive forces are the intermolecular forces that exist between like molecules, and the adhesive forces are the intermolecular forces that exist between unlike molecules. Now that is important. These two terms are important for us to understand the phenomenon known as capillary action, all right? Or, I'm sorry, I'm jumping the gun. The formation of a meniscus and the shape of it. Now, if you look at the meniscus, which is basically the surface of the liquid, right? Which is basically the interface between the air above the liquid and the liquid below it, right? If you compare the meniscus of water compared to the meniscus of mercury, you'll see that they're both concave in shape. But the difference is that the meniscus of water goes down and comes up, while the meniscus of mercury goes up and then comes down, all right? And we can understand the difference between these two as a result of the difference between adhesive forces and cohesive forces. So if you took into account what happens in the case of water, right? The intermolecular forces exist in water, of course, between the water molecules here, but there's a stronger attraction of the water molecules to the surface of the glass, all right? So therefore, as a result, since the adhesive forces in the case of water, the cohesive forces in the case of water would be weaker compared to the adhesive forces between the water molecules and the surface of the glass. The water molecules will be pulled up the surface of the glass, and as a result, the shape of the meniscus would be like this, all right? Now, the opposite would be true in the case of mercury, right? There are different forces that are occurring in the case of mercury compared to water. They're called metallic forces. And these forces are stronger compared to the attraction forces between the mercury atoms and the surface of the glass. And the result of that is that the mercury atoms would be pulled closer to each other within the mercury, beneath the mercury surface. And as a result, the shape of the meniscus would be like this, all right? So that explains the difference between the shapes of the meniscus in the case of mercury and in the case of water, all right? Now, the other thing I want to talk about, which I was jumping the gun to, is the phenomenon of capillary action. And I'm quite sure we're all familiar with this experience. If you take a very small tube in terms of the diameter, and one end is open, and you dip the open end in a liquid like water, then some of the liquid will move up into the tube. And that is because, again, of the difference in the strength of the adhesive forces compared to the cohesive forces. So the cohesive forces between the water molecules will be weaker. The adhesive forces between the water molecule and the glass surface will be stronger. And as a result, the water will be pulled up into the capillary tube. All right, so that's also a another phenomenon which is related to the difference between the adhesive forces and the cohesive forces. Okay, any questions so far? Any questions? Any questions? Okay, so moving along. Viscosity is also another phenomenon which is related to the attractive forces between the molecules in a liquid. Here's a definition of viscosity. It's a measure of a liquid's resistance to flow, and therefore the liquids that flow easily are said to be mobile, and we measure viscosity in units of poise, all right? And basically what you'll find is that the stronger the intermolecular forces in the substance, the greater will be the viscosity, all right? The liquid will be more resistant to flow if the intermolecular forces between the molecules are stronger, all right? And that's basically all we have to say concerning viscosity. Okay, so we talked about liquids, all right? So let's talk about the type of forces that exist in solids. Now, we're familiar with some of these forces already when it comes to ionic compounds. So we won't say much about that, but let me first talk about covalent compounds that display a particular strong type of force between the particles, and these are known as network covalent compounds, right? And basically, as the name suggests, what you'll find is that these compounds would have a network of covalent bonds that extend right throughout the solid, and as a result, it holds the structure together, and it imparts certain properties to these structures. These structures tend to be hard, they tend to have high melting and boiling points, and a good example of this would be the structure of diamond, which you see here on the screen, right? So if you look at the structure of diamond, you see that basically there's one unit that you can identify that is repeated throughout, and that is a tetrahedral unit where you have a carbon at the center, and it is tetrahedrally surrounded by other carbons around it. And that continues throughout the whole structure of diamond, all right? And these, of course, are relatively strong covalent forces. So collectively, the forces are very strong. And therefore, that's why diamond is the hardest known substance because of these strong intermolecular forces. And diamond also has a high melting point, high boiling point, and so on. Now, there's another structure of diamond. In fact, another structure of carbon which exists, right? In fact, there are several structures of carbon that exist in nature. Diamond is one of them. Another one is graphite. And okay, so that is diamond, all right? Each carbon is sp3 hybridized, by the way, in the case of the formation of diamond. And then there's graphite, and this is the structure of graphite. And if you compare the two, you'll see that the obvious difference between them is that in the case of graphite, it consists of sheets of carbon where they are arranged in a 6-membered ring structure, as you can see here. So you have one 6-membered ring structure here, another here, and that is repeated right throughout the whole structure, all right? You'll notice, however, that between the different sheets, there's no covalent bond that is connecting the carbons from one sheet to the carbons of another. So the result of that is that, well, and this is a consequence, I should say, of the fact that each carbon atom is sp2 hybridized. And what you'll find above and below each sheet is a delocalized system of pi electrons, similar to what we discussed earlier, all right? So the consequence of this is that unlike diamond, graphite is not as hard, and it actually has a kind of slippery field, all right? And the reason why the field is so slippery is because these sheets can move over each other very easily because there's no strong forces of attraction between the different sheets, all right? So these different forms of carbon, they're called allotropes, all right? And I think I gave the definition of allotropes earlier, which is basically the existence of 2 or more forms of an element that differ in their molecular structures, right? And carbon is one of them, and sulfur is another example of an element that can form allotropes, all right? So we say that these are 2 allotropes of carbon. And there are others as well. There's another one known as graphene, and there are several others. There's another type that exists in soot. So, you know, there are different allotropes of carbon, but these are the 2 main ones that exist in nature, all right? Okay, so this is basically a summary of the different types of forces that will exist in different types of substances. So we talked about the fact that in the case of nonpolar compounds, the major force that exists would be dispersion forces. And the properties that they tend to exhibit is that they tend to be low to moderate melting point compounds, and they tend also to be soluble in nonpolar solvents. And these are just some examples of such compounds, all right? And then the next type of force we talked about were the next type of compound are the polar molecules. And the major type of force that exists would be the dipole-dipole interaction. Now, let me just say that, as I said before, dispersion forces still exist when it comes to any covalent compounds, but these would not be the major players in terms of the type of intermolecular forces that exist. The major intermolecular forces would be the dipole-dipole and dipole-induced dipole attractions, all right? And again, these compounds tend to have low to moderate melting points. Some of them are soluble in nonpolar solvents and some are soluble in nonpolar solvents. And these are some examples of compounds which fall into that category, all right? Now, when it comes to these types of compounds, nonpolar and polar molecular compounds, the type of forces collectively, the dispersion forces and the dipole-dipole interactions collectively are called van der Waals forces. So these forces here collectively are called van der Waals forces, all right? So there are two types of van der Waals forces. You have the dispersion forces, and then you have the dipole-dipole, permanent dipole forces, all right? Okay, so the next type of force, of course, we talked about was hydrogen bonding, and this exists in molecules that contains hydrogen bonded to any one of these three elements, nitrogen, oxygen, or fluorine, all right? So hydrogen bonding would be the main type of bonding. And I should say here that the other types of bonding, dispersion forces also exist. So let me put this down here as well. But the main type of bonding would be the hydrogen bonding. And these are the type of properties that these compounds exhibit. And of course, these are some examples of compounds that will exhibit this type of bonding phenomena or intermolecular forces. And then we get to the network covalent type of compounds. These are covalent compounds or covalent bonds. And we saw the example of carbon and graphite, and some other examples are shown here, all right? So these compounds, what they have in common is that you have a large network of atoms that are covalently bonded to each other. And as a result, collectively, those covalent bonds imparts properties such as hardness, right? They tend to have high melting points, and they tend to be poor conductors of electricity. Oh, by the way, I should mention something. Speaking of conductors of electricity, in the case of graphite, these are very good conductors of electricity. Whoops, sorry. So graphite is a good conductor of electricity. And the reason why that is so, I should have mentioned this before, is because you have pi electrons here, which are delocalized, right? They're not shown here, but you can take my word for it. You have delocalized pi electrons, right? And these electrons will move under the influence of a potential difference. So basically, graphite is a very good conductor of electricity and is very useful, especially when it comes to electrolytic cells, because they conduct electricity without actually reacting with substances when electrolysis is taking place, all right? That's the nature of graphite. Graphite is the only non-metal that can conduct electricity very well, all right? Okay, so let me get back to this table here. And of course, we are familiar with ionic compounds, which are made up of cations and anions. The type of forces that exist between the ions would be electrostatic attractions. And as a result, they impart properties such as described here: high melting points, high boiling points, non-conductors of electricity as solids, but when dissolved in water, if they can, then they become very good conductors of electricity. And here are some examples of ionic compounds which displays that behavior. And then this one here, metallic, we didn't discuss this, but we can talk about it now. The metallic forces exist between the metals of pure metals, the metallic atoms, or I should say more specifically, the metallic ion or cations and the delocalized electrons. Now, let me explain what's happening here. And let me pull up my writing pad here so I can explain more fully. The type of bonding that exists in metals basically is the following. You have metallic ions. So you have, how am I going to do this? You have a metallic ion here, metallic ion here, metallic ion here, and so on and so forth throughout the whole structure of the metal substance. And then you have electrons permeating the between the spaces of the ions. So you have electrons. You have basically what is referred to in most textbooks as a sea of electrons between the metal ions, right? So that continues throughout the whole structure. So here, I'm just going to put the electrons here between the cations. So here we call this a sea of electrons, all right? So therefore, electrons. So therefore, you have a strong attractive force between these positive ions and the electrons that are flowing between them, right? And these electrons are very mobile. And that's the reason why electrons are able, that's the reason why metals are able to conduct electricity very well, all right? So going back to the table here, the bond that exists between the metals, the metal cation and the electrons, we call these metallic bonds, right? And as a result, these are the properties that, that are the result of the metallic bonding. You have hardness in most cases. Some metals are soft. The melting points vary from low to high. They tend to be shiny, they tend to be ductile, and they tend to be malleable. And of course, they tend to be very good conductors of heat and electricity. And of course, basically, metals are the substances that display these behaviors. And these are just some examples of metals that does that, all right? So that's basically a summary of the different types of forces that exist at the microscopic level within different substances. So if you're asked a question concerning this, more than likely the question will be about the type of forces that exist if you're given a substance. So for example, if I gave you, let me go back to my writing pad. If I gave you, let me clean this up. If I gave you, for example, H2O, and I ask you what are the major intermolecular forces that exist? Well, we know that water has hydrogen bonded to oxygen. So one force definitely that will exist would be the hydrogen bond. And the other force that will exist would be the dispersion forces or London forces, all right? Because dispersion forces exist in every molecular compound, all right? If I gave you, for example, carbon tetrachloride, right? Well, for one, we know that this compound here is nonpolar, right? Which means that the only force of attraction that will exist between the carbon tetrachloride molecule would be dispersion forces. All right? Let me do a couple more examples. Let's say you're given let's say you're given CH3Cl, all right? This is known as chloromethane. So the first thing we'd have to find out is whether or not this molecule would be polar. So what do you think? Is this molecule polar? Anybody? What do you think the shape of this molecule is? You have carbon bonded to hydrogen, chlorine, hydrogen, hydrogen. That's a Lewis structure of this molecule. You have some lone pairs of electrons here, but that's a Lewis structure. So what's the shape of this molecule? Anybody?
Like a tetrahedral pyramid?
Exactly. Tetrahedral. Okay, so if the shape is tetrahedral, right? That means that, and I'm going to try to draw the shape over here. Or let me draw it here. I should be able to fit it here. You have carbon bonded to chlorine, bonded to hydrogen here, bonded to hydrogen here, and bonded to hydrogen here. So that's a general tetrahedral shape, right? So would you expect this molecule to be polar?
Yes.
Exactly. So if the molecule is polar, then what would be the type of intermolecular forces you expect within this substance? Intermolecular forces. So what type of intermolecular forces you expect if the molecule is polar? Well,
what are you asking?
the type of intermolecular forces that exist, whether or not it would be hydrogen bonding or dispersion forces or ionic bonding or, you know, the chart I showed you before, this chart. Let me go, whoops, not that. This chart, right? What I'm asking is the type of forces that exist. Would it be dispersion forces or dipole-dipole forces or hydrogen bonds or covalent bonds? What would be the major force that exists between, bring this over here.
Would it be a hydrogen bond?
Well, that would be incorrect because remember we said that for a hydrogen bond, you must have oxygen bonded to hydrogen or nitrogen bonded to hydrogen or fluorine bonded to hydrogen. If you don't have these possibilities in the structure, then you won't have hydrogen bonding.
So it'd be the dipole.
Okay, so dipole-dipole interaction would be the most important intermolecular force, but also dispersion forces, because remember I said that for any molecule, the dispersion forces will always be there, all right? But it will be a weak force, right? The dipole-dipole would be the stronger force of attraction between these molecules, all right? Okay, let me do one more example. How much time do we have left? It's 10:19. Okay, let me do one more example and then we can move on to other things. Okay, suppose you're given, all right, here's an interesting question. You're given these two compounds. Okay, question is, which one has the higher boiling point and why? Which one of these two compounds have the higher, write this down, higher boiling point and why?
Would it be the CH3OH?
You're absolutely right. So what's your reasoning?
Because of the hydrogen bonds?
Okay, so the main type of force here in this molecule would be the hydrogen bond, but it will also have dispersion forces as well, all right? The main type of intermolecular force in this molecule would be dipole-dipole interactions, dipole-dipole forces, and also dispersion forces, right? And because the hydrogen bond is stronger compared to the dipole-dipole interaction, which is weaker when you compare these two, that means that this molecule, the methanol molecule, will have a higher boiling point. All right? So that's how we can explain the difference in the boiling points between these two substances, right? Because we know that hydrogen bonding would exist here because of the OH bond. All right? And that is stronger compared to the ordinary dipole-dipole interactions. All right, any questions about this? Any questions? Okay, some other ideas or examples just came to mind. So let me go through that while I have it fresh in my mind. Suppose you're given, how should I do this now? Okay, COH, H, 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 and COH, H, H, C, H, H, H. Okay, again, the question is, which one has the higher boiling point between these two, and why?
The one on the right.
Okay, correct again, why?
Because of the hydrogen bonds and dispersion, right?
Exactly. Well, they both have hydrogen bonds, right? They both have
Yeah,
the
but the one on
OH.
the right has more hydrogen bonds.
Well, no, there's only one. No, there's no difference in terms of the number of hydrogen bonds that can be formed because they both have one OH group. The difference between them, of course, is that this one has a longer carbon chain compared to this one, right? So let me just write here. Both have hydrogen bonding. Write that down here. However, because this one has a longer carbon chain, this has a greater dispersion forces. And this one has a weaker dispersion forces, all right? So therefore, as a result, this would have the higher boiling point, all right? So that's how we do that one. Any questions about this? Any questions? Okay, and another example just popped into my head, so let me do that now before I forget. Suppose I gave you, all right, okay, here we go. C double bond O, H. I remember giving this one to my organic class several years ago, and they hated me for this, for giving them doing a test. Let's see if you can figure this out based on what we just discussed. Okay, again, the question is which one has a higher boiling point? So higher boiling point. Which one would you expect to have a higher boiling point and why?
The one on the left.
Why? Why do you say that? I'm not saying you're right or wrong. I'm just asking why. I'm asking for the rationale that you're using to come up with that answer. All right, let me give you a little hint, all right? The difference between, okay, let's deal with the similarities. What they both have in common is the carbon to oxygen bond, right? And you know that that bond is polar, going in that direction here and going in that direction here, all right? Okay, the difference between these structures is that the carbon here is bonded to 2 hydrogens, while this carbon here is bonded to 2 fluorines, all right? So this bond here, as well as this bond, is essentially nonpolar, right? Carbon to hydrogen bonds are essentially nonpolar for most intents and purposes, all right? Now, the fluorine to carbon bond is polar in each case, right? So that means you have one dipole acting in this direction and another dipole acting in this direction, all right? So that's the situation in terms of the polarities of the bonds. So based on what I've just described to you, which one would you expect? Which molecule of the two would you expect to be more polar? Well,
It'd be the one on the right then, right?
exactly. Because what you'll find is that in this case, how should I put this? The dipole moment, the net dipole moment, let me put here, net dipole moment for this one would be less than the net dipole moment for the other one, right? Because if you look at the directions of these dipole moments, they almost cancel each other out, all right? Not exactly, because we know that oxygen is different from the fluorines, but because of the trigonoplanar arrangement of the bonds, then basically these dipole moments will oppose that dipole moment, and therefore the net dipole moment will be less compared to what we have here, where you have a dipole moment here, but they won't be opposed by any dipole moment from the CH bonds, all right? So as a result, hold on, maybe I misspoke. Hold on, let me see here. Actually, you were right the first time, my bad. It is this would be more, would have a higher boiling point, all right? Because the net dipole moment here is greater, which means that the dispersion forces would be greater. Dispersion forces here would be greater than the dispersion forces for the next one. So I apologize for that. That's my mistake. All right. The one with the greater net dipole would be the one with the greater dispersion forces, and therefore the one with the higher boiling point. All right. Okay. Any questions about this one? Any questions? All right. So these are the kind of questions you can get when it comes to this topic, right? Questions can come in different forms. You could be given a series of compounds, for example, and asked to arrange them in order of increasing or decreasing boiling points, melting points, etc. So it all depends on, how the question is posed. Okay, so much for that. All right, so let's talk about crystal lattices, and this is going to be the last topic in this chapter. And this has to deal with the formation of crystalline substances. And what crystalline substances all have in common is that if you look at their microscopic structure, you can identify what we call repeating units. So in other words, you'll find a pattern within one particular unit, and then you see that pattern repeated in subsequent units, all right? So for example, you can have, this is a structure of graphite, for example. We saw this earlier. As you can see, you have 6-membered rings that are basically joined or sharing one side, sharing 2 atoms. And if you go from left to right or top to bottom, you see basically repeating units existing in this structure, all right? So that's an example of what we call a crystal lattice, all right? Here's another example. This is basically a simple cell, a simple cubic arrangement. And some ionic compounds exist like this. And as you can see, you can identify one unit cell, and that unit cell is repeated in 3 directions, X, Y, Z, if you will. All right, so that's another example of a unit cell. So we see this a lot in, different solids, mainly, of course, usually in ionic compounds, and sometimes in the case of covalent compounds. All right, so let's define, let's look at unit cells, in some examples of unit cells. So the simplest one is called a simple cubic cell, and that's basically where you have the atoms or ions at the corners of a cube. And then one which is a bit more complicated is called the body-centered cubic structure, BCC for short. And basically you have the same arrangement as this, excepting there's an extra atom or ion at the center of that cubic arrangement. So that's why it's called the body-centered cubic arrangement. And then you have what is called the face-centered cubic arrangement, which again is similar to this, excepting that instead of having one atom or ion at the center, you have one atom or ion occupying the face of each face of the particular cubic arrangement of the other 4 atoms, all right? So that's called the face-centered cubic structure. Okay, another definition I need to introduce to you is what is known as the coordination number, excuse me. And the coordination number is basically the number of nearest neighbor particles to a single atom or particle in a crystal structure. So for example, in this simple cubic structure here, you have this atom here, and the nearest atoms or ions to this one would be these here, the red ones, right? So therefore the coordination number is equal to 6 in the case of the simple cubic structure, all right? Now, what we're going to look at is the type of, the different possibilities in terms of how these particles are packed, all right? And if you're looking at one layer situation, then there are 2 types of packing. You have what is known as the open packing, which is shown here on the left, and then you have what is known as the closed packing. And if you look at these closely, you'll see that the closed packing has a greater amount of contact between the particles, right? You have more spacing that you can identify in the case of the open packing, whereas in the case of the closed packing, it's a more compact arrangement. And this is more likely to be the case compared to the open packing for most structures. Now, once you have established the layer situation for open packing, for closed packing, I'm sorry, then what you have to look at is how will the other layer be arranged. Now, in order for us to do that, we have to make a distinction between what are known as the tetrahedral holes and the octahedral holes, all right? Now, basically, when the other layer is placed, right? So here we have the first layer, which would be the red spheres, and then we put the other layer above it. You're going to identify these 2 different types of holes. So the tetrahedral holes are the ones that are located above a sphere in the bottom layer, which would be here, here, and here in this particular diagram. And then we have the octahedral holes, which are located above a space in the bottom layer, which would be here, here, and here, all right? And it would be here if there's another sphere here, would be here if there's another sphere here, all right? So it's very important that you understand the difference between the octahedral hole and the tetrahedral hole in this structure here. And the reason why that's important is because when it comes to stacking the next layer, what you'll find is that there are 2 possibilities in terms of where those spheres will end up. Now, if the spheres end up above the hold on, give me 1 minute here, let me check something here. If you have a sphere stacked above the tetrahedral holes, then the resulting structure would be called the hexagonal closed pack structure, all right? When the spheres cover the tetrahedral holes, right? So this is what it looks like from above, and if you were to turn it sideways, it's going to look like this. And you'll notice that basically as you go from one layer to the next, you have a repeating, you have a repeat situation for every 2 layers. So if you label the first layer A, the second layer is labeled B, then the second layer is labeled A because it has the same arrangement as the first layer. And that is basically what continues as you go down. If you're looking at this HCP arrangement, it's going to be an AB sequence, all right? Now, if you have the next layer, instead of covering the tetrahedral hole, it covers the octahedral hole, then you're going to end up with what is called a cubic close pack arrangement, right? So that's what we're showing here. And if you turn it sideways, it's going to look like this. And in terms of the repeat arrangement, what you'll find is that as you go from bottom to top, it's going to be one arrangement here, a different arrangement for the second layer, a different arrangement for the third layer, and then the fourth layer would be the same arrangement as the first layer. So basically we call this an ABC, ABC, ABC arrangement as you go from the bottom to the top, all right? So basically as stated here, this sort of arrangement produces a 3-layer repeating unit situation, all right? So those are the two different types of close packed structures that one can identify. So which ionic structures tend to adopt the different type of structures? Well, it depends, as you can see here, on the ratio of the cations to the anions, right? So as stated here, smaller cations can fill the voids between the larger anions, right? So when it comes to the tetrahedral hole filling, what you'll find is that the ratio of cations to anions would be from 0.225 to 0.414, right? So if you have a situation where the ratio here falls within this range, then basically you'll have tetrahedral hole filling occurring. Now, if the ratio falls within this range from 0.414 to 0.732, then basically you tend to have octahedral hole filling occurring. And down here it says that basically the arrangement would be cubic if the ratio that we just talked about will be above 0.732. So basically this is the criteria that is established in order to predict the type of hole filling that will take place in a different type of packing, CCP and HCP. Okay, so just to give you two examples of ionic compounds which displays these different type of arrangements. If you compare cesium chloride to sodium chloride, you see that in the case of cesium chloride, it would be a body-centered situation where you have the central atom or central ion, which would be the chloride ion, and it is surrounded by, as you can see here, 8 chloride ions, all right? The ratio here is still 1-to-1 between cesium and chloride. The formula for cesium chloride is CSCl. And the reason why it's still 1-to-1 is because basically each of these unit cells will be sharing 1/4 of a chloride ion here, 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 here. Actually, not 1/4, 1/8, my bad. 1/8 here, 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 1/8 here, 1/8 here, and 1/8 back here, right? And since you're 8 of them, 8 times 1/8 give you 1. So therefore, that's why the formula indicates that there's a 1-to-1 ratio between the cesium and the chloride ions, all right? And then now, in the case of sodium chloride, this is a face-centered arrangement because if you look at, for example, the sodium ion here, right? In fact, if you look at the whole structure here, which is a unit cell, basically you'll see that the face will have at its center a chloride ion here for this face, here for this face, here for that face, and here for that face, all right? So that would be the arrangement, and here for this face, and here for this face as well, about those two, all right? So basically we call this a face-centered structure, all right, in the case of sodium chloride. So it all depends on, of course, which ions are involved and the ratio of the cation to the anion in each case, all right? Okay, I'm going to skip this here. This has to do with basically how these structures are experimentally determined. This is basically dealing with a phenomenon known as X-ray diffraction. And it's not very easy to, well, it will take a long time for me to explain this. If you have to do physics, you will definitely encounter this phenomenon, and you'll probably understand it more when it comes to using this to determine the three-dimensional structures of crystals, all right? Okay, so that's basically it for this chapter and for this course, all right? So you might be wondering what we'll be doing for the rest of this time, for the rest of the semester. Well, basically, there is, well, for the next class, I'm going to have a regular lecture because I want to look at some examples dealing with crystal structures. So make sure you come to class for that. And after that, for all the other classes that we'll be having, I will make myself available on Skype during class time. All right, so if you have any questions you want to ask, any issues you want to clear up, you can contact me during that time for that purpose, all right? So that's basically, oh, and before I forget, let me remind you, I've posted test number 3 in Canvas. So make sure you go there, download it, and print it and complete it. And I think the deadline I set is Friday. So make sure that you submit it on Friday so that I can have it to grade and send back to you, all right? Make sure you do it in ink. Make sure you scan it and send it as a PDF document. Yeah, and that's it. Are there any questions you have for me? Any questions? Any questions?
Sir.
Okay, if there are no questions, then that's it for today. Enjoy the rest of your day, and I'll see you guys on Thursday. All right, so take care.
You too.
All right, bye.